Hello and welcome back. In section 2.1, we start to look at an intro to limits. So we'll start with a piecewise defined function. So f of x is going to be 2x if x is strictly less than 0, and it will behave as x plus 4 if x is at least 0. Alright, so I'm not going to put a lot of detail into the sketch of this. I just want to kind of show the highlights of what it looks like. So both of these pieces are linear. So if x is less than 0, so in other words we're over here to the left of the origin, the graph acts like we had the equation y equals 2x. So we can get very close to 0 but not reach it. If we plugged in 0, 2 times 0 is 0, we would hit the origin. So instead of hitting the origin, we get close to the origin, and then we have a slope of positive 2. So there is part 1 of our piecewise sketch. Part 2, we have a y-intercept at 0, 4. Because of the or equals, we actually get to use it, and we have a slope of positive 1. And we're going to the right because of the criteria that this is true when x is at least 0. So the idea of limits, instead of saying what's happening at a point, it's saying what's happening near a point. So for this graph, the limit as x approaches 0 from the left-hand side, so this superscript negative is telling us we're coming at it from the left side. Our function is f of x. The y value we're getting close to is 0. So even though we don't actually reach that value, the limit is just saying what do we get close to? We get close to 0. Now if I look at the limit of this function f of x as x approaches 0 from the right, would get a plus superscript. So coming in from the positive side and heading towards x equals 0, we get closer and closer to 4. This left side is sometimes referred to as the left-hand limit and right-hand limit. Now since these don't agree, then if I'm asked for the limit as x approaches 0, no superscript, just the arrow and the number, function f of x, I would say that it does not exist. Usually that's abbreviated DNE. So that limit does not exist. I can't say as we get close to 0, again not specifying sides, as we get close to 0, the y values get close to some number. If they do agree, then the limit does exist. So for this next one, we already used f of x, so let's call this guy g of x. So g of x is going to be 3x plus 1 if x is less than 0, x squared minus 2x plus 1 if x is greater than 0, and negative 4 if x is exactly equal to 0. So again, I'll do just a quick rough sketch of what this piecewise function will do. So x less than 0, so that's over here on the left side. 3 times 0 is 0, 0 plus 1 is 1, so we get close to the point 0, 1, and we have a slope of positive 3. And in fact, we can start our work with limits with that fact. So the limit as x approaches 0 from the left of function g of x is equal to 1. You might recognize this x squared minus 2x plus 1 as a perfect square trinomial. We can factor that into x minus 1 quantity squared. So that is a parabola shifted to the right 1 unit. And again, we're only allowed to get close to 0 for that one. Well, 0 squared is 0. Negative 2 times 0 is still 0. And plus 1 also takes us close to 1. So we can say that the limit as x approaches 0 from the right of function g of x is also a positive 1. Now it just so happens that at 0 we have negative 4. So g of 0 is equal to negative 4, but the limit as x approaches 0 of function g of x is a 1. So these don't necessarily have to agree. You may have two different values. The limit is talking about what's happening near the point, whereas g of 0 is saying what's happening when x is exactly equal to 0. So on the coming in from the left side or the right side, we're heading close to the value of 1. At the actual point, though, our output was negative 4. All right, so let me give you all one to play with. P of x is going to be a 3x plus 2 if x is strictly less than 3, 10 if x is exactly 3, and a 4x minus 1 if x is strictly greater than 3. So see if you can make a quick sketch of that. This time the key point being at x equals 3. And take a look at the left limit, right limit, the limit, and the value at 3. Okay, welcome back. So we'll do our sketch here. All right, so if x is less than 3, it behaves as 3x plus 2. So getting close to that, 3 by 3 is 9 and 2 is 11. So we get close to 311, and we have a slope of positive 3. We have an output of 10 if we're exactly at 3. And 12 minus 1 is 11, and a slope of 4. So a little bit sharper of a positive slope. So your sketch should look something like that. So our limits, the limit as x approaches 3 from the left of function p of x. From the left side, we are approaching a y value of 11. 3 by 3 is 9, plus 2 is 11. Limit as x approaches 3 from the right of function p of x. From the right side, again, we're also getting close to 11. P of 3, however, was 10. And the limit as x approaches 3 of function p of x, since the left and right side agree, our limit is 11. So as long as your left and right limits agree, you do get to say we have that limit. If the left side and right side do not agree, the limit does not exist. All right, so next we'll take a look at a rational function. You might recall we were temporarily skipping the rationals until we got to play with limits. So here we are back with rationals, now dealing in limits. So we'll do f of x is the reciprocal of the sum of x and 5 increased by 2. So we'll start by looking for f of negative 5. F of negative 5 gives us a division by 0. So that is undefined. They may ask us, though, for the limit as x approaches negative 5 from the left. So this negative sign is from the fact that I'm approaching a negative number. This superscript one is saying approached from the left-hand side, and our name still is f of x for this guy. So as we approach negative 5 from the left-hand side, if we want to think of this numerically, negative 5 plus 5 is 0. So something very close to negative 5, but a little bit to the left will be negative 5 with a little bit more negative stuff left over. So this will be 1 divided by some very small negative number. Recall, if you divide by a smaller number, your output will get bigger in absolute value. Think of just a basic 12 divided by 4 is 3, 12 divided by 3 is 4, 12 divided by 2 is 1, 12 divided by 1, 12 divided by 2 is 6, 12 divided by 1 is 12, 12 divided by a half is 24. As you divide by something with a smaller absolute value, your results get bigger and bigger. So this is having us approach negative infinity. Negative infinity plus 2 is still negative infinity. So we have a positive 1 divided by a very small negative number. Next, we'll look at the limit as x approaches negative 5, this time from the right side, for function f of x. So this time, we have negative 4.999999993. Something very close to negative 5, but a little bit to the right of it. That's going to give us a very small positive number, which will be a constant divided by something approaching 0 in size. We approach infinity for our quotient, this time positive. So this is positive infinity. Left and right side limits do not agree. So the limit as x approaches negative 5, the function f of x does not exist. Now, one other thing that they may ask us with respect to limits and these rationals, they might ask us what's happening near infinity. So they might ask us the limit as x approaches infinity of function f of x. So now instead of our denominator getting infinitesimally small, our denominator starts getting bigger and bigger. So again, think back to our little table here with the 12s. If our denominator is getting bigger, our quotients would be getting smaller in absolute value. So this will approach 0. 0 plus 2 is 2. Alright, so let me let you all play with a rational. We'll do g of x is 1 over x minus 2 quantity squared plus 3. So I'm going to have you find g of 2. Limit as x approaches 2 from the left of g of x. Limit as x approaches 2 from the right, g of x. Limit as x approaches 2 of g of x. And the limit as x approaches infinity of g of x. So go ahead and pause that and pop back in when you're done. Okay, welcome back. So our first one, g of 2, we get division by 0, which is undefined. So g of 2, undefined. As we approach positive 2 from the left-hand side. So we're talking 1.999997. So the negative is slightly larger. So we get an infinitely small negative value, but when we square a negative, we are kicked back over to a positive. Division by a very small value gives us a large result. So this is infinity. Similarly, approaching 2 from the right side, now I have the positive side is slightly larger. So I have a very, very, very small positive value. Square that, still positive. Constant divided by a small positive will give us, have us approaching infinity. Left and right sides agree. So this limit is infinity. So whether approaching from the left or right side, our graph will approach infinity. And then as x goes to infinity, again, that's making our denominator this time infinitely large. If you divide by a constant by a very large number, you'll get that term close to 0. 0 plus 3 will give us a 3 as a solution. Now sometimes we will need a little bit of algebraic manipulation. For example, maybe we're given f of x is x squared plus 5x plus 6 all over x plus 2. So they may ask us for f of negative 2. That has us dividing by 0, so that is undefined. They may also ask us for the limit as x approaches negative 2. So if I plug it in as is, we have 4 minus 10 plus 6. Well, that's a 0 up top and a 0 at the bottom. If we have 0 over 0, we call that the indeterminate form. So what I'm going to do is manipulate it. We'll do a little bit of factoring. So x plus 3 by x plus 2 upstairs, x plus 2 downstairs. And for x not equal to negative 2, this is then equal to x plus 3. If x is negative 2, all bets are off. That's why this is still undefined. But if we want the limit as we get close to there, now I can plug in the negative 2. Negative 2 plus 3 is 1. We will get close to 1, but we cannot actually reach 1. Maybe I'll try a couple of these out. I'm going to try the limit as x approaches 1 of x minus 1 over x squared minus 1. Okay, so this one, hopefully you saw we were in the indeterminate form. Zero at the top, 0 at the bottom, so then this is equal to the limit as x approaches 1 of x minus 1 over x plus 1 by x minus 1, which is the same then as the limit as x approaches 1 of 1 over x plus 1. Now I can plug in the 1 and I get 1/2. So this limit does exist and it's worth 1/2. They may ask us for the limit as x approaches 1 of, let's say, x minus 1 squared over x squared minus 1. We're still in the indeterminate form, 0 over 0 if we plug in a 1 top and bottom. So I'm going to hang on to that limit. Limit as x approaches 1. Now we have x minus 1 by x minus 1 over x plus 1, x minus 1. I can knock out one set of the x minus 1s. So then I have the limit as x approaches 1 of x minus 1 over x plus 1, which gives me 0 over 2, which is 0. So the limit does exist, and it's the number 0. Next one, we'll take a look excuse me, at limit as x approaches, we'll keep it at a 1 still. We'll do x squared minus 1 over x minus 1 quantity squared. So we can get the indeterminate form, 0 over 0 still. So a little algebraic manipulation, x plus 1, x minus 1 over x minus 1, x minus 1. So just expanding out what the square actually means. Again, we can drop one set of them. So now we have the limit as x approaches 1 of x plus 1 over x minus 1. But that would give us 2 divided by 0. So this limit does not exist. I can't do any more algebraic manipulation to this. On the left side, I would approach negative infinity. Right side, I would approach positive infinity. The limit does not exist. Since those don't agree, that's why we're saying this limit does not exist. All right, so the next idea that we look at in this section is the limits of the difference quotient. That's something that we worked with before in our algebra review, but without the calculus context. So difference quotient is going to be the limit as h approaches 0 of f of a plus h minus f of a all over h. So it's as h approaches 0, not h is exactly equal to 0. So for example, we'll take a look at f of x is 8x minus 2. And we'll take a look at the difference quotient at, let's say that a is equal to 9. So we want then the limit as h goes to 0 of f of 9 plus h minus f of 9 all over h. So 3 pieces, I'll find each piece and then plug them in. So let's find f of, and we'll start with the simpler one, f of 9. So 8 by 9 minus 2, 72 minus 2 is 70. F of 9 plus h, 8 by something minus 2. This time my something is the entire quantity of 9 plus h, and then we simplify. So f of 9 plus h, we have 72 plus 8h minus 2, which is 8h plus 70. So now I have all 3 of the pieces that I need. So this difference quotient, I would take the limit as h approaches 0 of, up top we'll have 8h plus 70 minus f of 9. F of 9 was 70, and h at the bottom. So the limit is h approaches 0 of, so notice 70 minus 70 is 0. That'll drop out. 8h over h. The h's will cancel. So the limit as h approaches 0 of 8 is just 8. Alright, so next we'll take a look at one of these, this time involving a square root. So this time f of x will be the square root of the quantity 3x. So this is defined on any open interval involving positive numbers. So in other words, it's defined at 0. So any of my values from 0 to infinity, I can find a value of f. I can't straddle 0 itself because I don't have anything to the left of 0. If I wanted to sort of pick a point to surround, if here is my a can't be 0 because this function doesn't exist to the left of 0, and I need to be able to make a little neighborhood around the point when I'm doing these difference quotients. So for this one, let's pick out a equals 5. So the difference quotient would be the limit as h approaches 0 of f of 5 plus h minus f of 5, all divided by h. So let's find each of the pieces. F of 5, nice and quick, square root of 3 by 5 is root 15. F of the quantity, 5 plus h, square root of 3 by something, that something is 5 plus h. So notice I'm not just tacking a plus h on after f of x. So make sure that you remember f of x with a plus h is not the same as f of the quantity, x plus h. Alright, so a little bit more simplifying on that. F of the quantity, 5 plus h, square root of 15 plus 3h. So now we've got all 3 pieces. So at the limit as h goes to 0 of square root of 15 plus 3h minus square root of 15 all over h. Now if I plug in 0 at the moment, I get 0 over 0, that indeterminate form. I'd like to be able to get something that's more useful to us. So what we can use here is the idea of the conjugate. So think back to your college algebra and intermediate algebra days when you were rationalizing denominators. This time, though, we're going to rationalize a numerator. So we're going to multiply top and bottom. It's two terms, so I'm going to group it in parentheses, by the conjugate of this one that has a minus in between. So that'll be the same thing with a plus in between. So root 15 plus 3h plus root 15. And if I do something to the top, I will also do it to the bottom. That way I'm multiplying by something worth 1. So I'm changing the look, but I'm not changing what it's actually worth. All right, so upstairs we've got a little work ahead of us. We're foiling that out. Square root of 15 plus 3h by a square root of 15 plus 3h will give us 15 plus 3h. So that's our first times first. Outside times outside, I'll have a plus root 15 plus 3h. Inside times inside, I'll have a minus of that same thing. And there's some nice, neat, pretty canceling happening. And last times last, negative by a positive negative, and root 15 by root 15 is 15. So those middle terms will drop downstairs. I'll just leave it factored for the moment. All right, so upstairs, with that middle part gone, I have a 15 minus 15. That is worth 0. So now I have the limit as h approaches 0 of 3h over h times our root 15 plus 3h minus plus root 15. H over h is 1 as long as h is non-zero, and by saying this is a limit, we're saying we're approaching but not reaching 0. So now I want the limit as h approaches 0 of 3 over square root of 15 plus 3h plus square root of 15. Now I can let the h go to 0. 3 times 0 is 0, so I have root 15 plus root 15. So that is 3 over 2 root 15. And then we just do a little rationalizing with that. So multiply top and bottom by root 15. And our limit as h approaches 0 would be 3 root 15 over 2 by 15, 30. So that would be root 15 over 10. So 3/30 is a tenth. So anytime we're doing the square root one, we're going to use a little bit of work with the conjugate. Let me give you all one to play with. So your f of x is going to be 7x squared plus 2x plus 1. And we're going to let a equal 4 here. So go ahead and find that difference quotient for, again, a equals 4. Okay, welcome back. So our difference quotient, limit as h approaches 0 of f of 4 plus h minus f of 4 all over h. So we'll find our pieces, f of 4. So you have 7 by